The music of atoms. What's that then? Well, we're talking atomic physics here. We're talking energy levels. We're talking a hydrogen atom and the behavior of the electron and how it explains spectra. I really like this particular topic. It's one of the last things I do at the end of the course, and I like it because it's lots of different things come together. It's lots of different branches of physics kind of joined together to explain something. And at the end of the two videos, we actually we calculate the radius of a hydrogen atom, which I think is pretty mind-blowing. Okay, so I do enjoy this topic. I think it's very, very interesting. So, the music of atoms. At the beginning, first of all, light comes from excited atoms. Imagine an atom snoozing. It hasn't got any extra energy. It's in its ground state. And for some reason, it becomes excited. It has gained energy. There's lots of ways you can excite an atom. You can bash atoms into each other. You can bash them with electrons. You can shine radiation on them and they can absorb energy from that radiation and they become excited. Then an excited atom can lose its energy by giving off a photon. And when it does that, the atom falls back to its ground state. They lose the energy in packets called photons and drop to a lower energy level. And then the lowest energy state is called the ground state. We can represent what's happening with an energy level diagram. There's the ground state at the bottom. An electron jumps up to a higher energy level. That's called excitation. Then the electron falls back down again at some point in the future and it emits a photon. It gets rid of this extra energy. This is the emission spectrum of hydrogen. This is the wavelengths of light, the visible wavelengths of light given off by excited hydrogen atoms. It's called the Balmer series. And it shows the visible light emitted by hydrogen atoms. Now, all hydrogen atoms give off these wavelengths. Okay? And why these wavelengths? Well, why do all hydrogen atoms emit the same wavelengths of light? And why these wavelengths? Is there any kind of pattern? And we'll be answering that in my second video. Let's talk a bit more about energy level diagrams first. There's actually lots of different energy levels within the hydrogen atom. We say that the lowest is the ground state, and that's n equals 1. Then there's n equals 2, n equals 3, n equals 4, etc., etc., up to n equals infinity, which represents ionization. If an electron gets to the n equals infinity, then it has escaped. Excitation involves an electron moving to a higher energy level, and then if an electron falls back down to a lower level, it gives off a photon. Let's actually put some numbers on these energy levels. Notice that we give them negative numbers. The ground state is minus 13.6 electron volts. N equals 2 is minus 3.4 electron volts, etc. Now, the ionization energy of hydrogen is 13.6 electron volts because that's the amount of energy you would need to give to an electron at n equals 1 to enable it to escape. Now, if an electron falls from one level to another, for example, if an electron fell from n equals 4 to n equals 2, then looking at the difference between these two energy levels, you'd get a photon with energy 2.55 electron volts. And using E equals HF, you can actually work out the wavelength. And if you do that, you get 488 nanometers. If I go back a slide, 488, well, that's looking like the green line in the emission spectrum. Okay. Is there a pattern in these numbers? Well, a pattern was developed. Somebody realized what the pattern was. It wasn't a very straightforward pattern until it was realized that these hydrogen atoms were actually also giving off ultraviolet photons, and that's called the Lyman series, the ultraviolet photons. And when that was discovered, and it was realized that n equals 1 was equal to minus 13.6 electron volts, then the pattern is actually very simple. And the energy of a particular level n is equal to minus 13.6 electron volts divided by n squared. So for n equals 1, it's minus 13.6. For n equals 2, it's minus 13.6 divided by 4. For n equals 3, it's minus 13.6 divided by 9, etc. There's still an important question that we will answer in the next video. Why are the electrons only allowed to have certain amounts of energy inside the atom? I mean, a planet in orbit around the sun can be at any radius from the sun. Why is an electron only allowed to have a certain radius? Why can't it have any amount of energy? Here's a question for you to do, a very typical kind of exam question. I'll let you pause the video, have a read, and I will show you the answer in 3, 2, 1. There you go. So the answer to part A, as I suggested earlier, it's going to be an ultraviolet photon because it's falling to n equals 1, so 103 nanometers. And then 1.9 electron volts, looking at the numbers, is going to be from n equals 3 to n equals 2.